next week, there's no class. Although you do not have any plan to do. You have plan, right? Yeah, I know. You guys need to do homework, assignments, and group projects. Not only for this class, but you might have 2 or 3 other classes. And also those who wants to practice or wants to apply for the NSA positions need to develop the projects very seriously. Okay, then you might have a very high chance to get in. So far, 3 of our students got in NSA through the demonstration. Yeah, some other students went through the regular interview process, but if you give a demo and if you make them satisfied, then your work will be appreciated by them. Okay, that is a good channel. It's a very, very, very rare channel that you can apply. Scheduling, we do not have many weeks as I calculate. 17th, this is mid-November, but next week is Thanksgiving. So when we meet again next time, that is December the 1st, already December, which means we have December 1st, 8th, 15th, and 22nd. 22nd. So 22nd is the day that we meet, or I'm not sure. 22nd. 23rd is the last day. So 23rd is the school still remains open, right? So maybe 22nd will be the day for you to make your presentation, group project presentation. And then week before, 15th, will be your exam. You have one exam.
Take home?
Take home.
Don't make it hard, please.
It's take home.
Take home is always harder.
Of course.
It's like 2, 3 papers.
No.
You mean take home with the multiple choices?
Alright, so I think we can all agree that none of us want to write 2 papers for a final, right?
Yeah.
No, it's going to be more than 2 papers for sure.
Stop that. Stop. I meant 2 papers, not taking 2 pieces of paper. I meant writing 2 full-on, like 20-page papers. No.
2-page papers.
I would like multiple choice, short answers. Maybe some of those long answers.
Online.
Maybe. I just don't want to be writing.
I like papers.
Multiple choice online.
Yeah, online, yeah. Everything, you can do whatever you want, but do not discuss among yourselves.
Okay.
At one case, then I may give for all fail, but I didn't do that at that time. Everybody has one answer.
Alright guys, no matter what, answer
Then
what to say.
I can claim that this guy is technically impossible to have the same answer by all the students, right? So that is illegal.
So if you don't want that to happen, put multiple choice. So
That is the reason I don't give you multiple choice, but I ask you to write. So when you write, it should be different.
If you don't want to
There's
see
only so many ways you can rephrase the same thing.
I know. But if you don't want to see same answer, put multiple choice.
If you want to see something true, you need to ask us why we're all here.
Evans, what are you trying to do? Your name is recorded here right now. Okay, so only reason I am giving you test is because to prepare your final exam. What doesn't matter what kinds of test exam. For that, everybody's really unhappy, but anyway, they can study. Right? Somebody studies very hard, somebody studies a little bit, but that is only the points they can go back and review the subjects they learned, right? So it is essential. And also, when you have an interview, if it is very decent positions, and if that is very high-tech development positions, then they probably would like to do wireless communications and cell communications or Wi-Fi. Then they may ask you some questions. All the materials that we cover here is really deep level. So not only the class exam preparation, but also your job interview preparation. This is the time that you can review some materials. Okay. So test will be 15th. Then we have only, after this, we have only 2 lecture. One over 2, or almost 2, will have real tech night, hands-on. So one thing that I ask you to do, because I've done many times successfully, there is a wireless communication, so that I'll give you transceivers for each team. So one guy can send data, then the other guy can receive, and also they can some encrypt the data and send, and 3 of those, 2 guys communicate. They know how to decrypt or how to encrypt. The other guys may not know, but may be able to receive. Then how, if they're lucky, then they can decrypt it, right? That type of things definitely will do. But it takes maybe a week. If you follow well. If you follow well.
You're going to bring an Arduino?
I need to inventory how many Arduinos that I have. But if you have Arduinos already purchased, bring your Arduinos, so that if we do not have enough Arduino Unos, then somebody may be able to use, right? I don't, because as I distribute, I lose
Pieces?
some pieces. Yes, students do not return.
Write down the names. Send them a bill.
Inventory each piece.
But I don't do that. I mean, somebody who wants to keep,
It's not good.
then with that, he can succeed his career. That's okay. Okay. Then eventually, if he becomes the CEO, then he may, at that time, he may recall that, I used some products from Mercy. This time I want to reward that amount times 5,000 or 50,000.
If he or she does that, you might not get a job, because when you do the background check, they ask you, have you ever done something
No, I
like
didn't.
that?
I didn't report it.
Yeah, if you don't report it, he or she might be asked that question, and you cannot say no, and if you lie, you don't get it.
What's that, a
So,
bribe?
what?
Was it kind of a bribe or?
No.
Yeah, some background check. They come to me and ask
It's
about
very
this.
simple, you won't even think about it, but it's still a fact.
The problem is that I do not know who took it.
But he or she might.
I do not want to know who took.
The rug took it.
Okay, so let's try to finish up cell communication today. we'll do a little bit of the cell, the concepts of cell communication. And then cell encryption. So encryption technique that we learned the last time, and also I want you to complete as your another homework assignments, right? So this is a little different. So you will see which one you like. All right. Last time we tried to see all of this may be challenged by this question. What would be the minimum distance between the centers of two cells with the same band of frequencies if a cell radius is 1 kilometer and the reuse factor is 12? If we have a 12 factor, then it will be like this, right?
Half a mile.
Okay. This. So I have here, if I have, let's say, we have a frequency, so 12 channels may be used, which means if we have a frequency band, then can be split into 12. But within this cell, you do not allow them to use, for example, if you are here, so that if you use channel 2, then none of the neighbor cell has the same channel. They're all different channels, right? So with the 12 channels, they can use exclusively. But anyway, that is the factor 12. Okay. This is radius, 1 kilometer, which is uppercase all in our notation. So in this definition here, okay, d over r equals square root of 3 times n. Square root comes only here. Okay. So why? So next two slides explain that. Say this is a small d, which is the distance between the adjacent center of cells. Distance between the centers of adjacent cell, like this. And we know this is radius, uppercase R, which is like, this is also R, right? But if I take only somewhere these parts, then it will be like this, okay? And because we have hexagonal, from here there, that is a 60 degree, right? And half of them is a 30 degree. This is 30. So back here, that is a 30 degree. This is a 30, and this is a 60. And this is right angle, 90. I want you to recall trigonometry of your high school. I know everyone loves trigonometry. Anybody hate
I just like
this?
it.
You like? Oh, you now like?
I love it. I like it.
Okay. And there is a rule, 30, 60, 90 triangle rule. You know that. Then the the length of three sides will be in this ratio: 1, 2, and square root 3. Sounds familiar? Yeah. Some Indians, of course, right? Oh, you are in part of, right?
Professor, not every Indian is good with math.
Alright.
It's
You are directly from India, right?
Yeah, both are from India, right?
Yeah. So trigonometrics is just cake, right?
You're supposed to be in high school after I've been brainwashed. Taught this. I would have been great at it.
But this is time that you can recall. Okay.
Recall, dude,
Yeah.
high school was like 6 years ago.
6 years ago. Oh, that's brand new. You're a
Right?
brand new graduate compared to someone else here.
After watching you, brand new.
Thank you.
We're not math majors, so it's not like fresh in our heads.
Oh, is it really difficult to math?
How,
It's not really
Yeah,
difficult
it's
math, right?
Python.
Like you
Yeah,
said,
it's just,
it's
yeah. If you do not
You don't use it.
call, but
7 since I last had math class. Because they
okay. So this is the right time for you to
to learn.
take a 5 minutes to think about triangle rules. 30, 60, 90 degree rules.
Triangles sharp, I can throw them.
Okay. So this is a shape that I took from here, right? This is the triangle. Exactly same triangle can be found here. So this is the triangle that I rewrite here, right? This is the triangle. Okay. So what is the distance in this case? The distance between the centers of an adjacent cell, small d, this is a small d, right? From here, there's a small d. And look at this triangle. Which one is the radius of that cell? If it is a circle,
A
cell,
squared plus b squared equals c squared.
Big R.
Right?
all,
That's the area? A squared plus b squared equals c squared?
Printed, yeah, that's the.
So if we do that,
exactly, yeah, that is, yeah, it comes from there, right? You're right. So you can, you have very long memory. You said 7 years old, 7 years old, yeah, 7 years old. So you can apply. Evan, you can apply. Here, a square plus b square, that is b square. So square root and square. If it is the case of 2 square, right? That is what you're saying.
which is true.
Is that true? Yeah, 1 plus
Square of the
3
root cancel out.
equals 4. Yes, you're right.
Woohoo!
Isn't that the Pythagoras?
Yeah, Pythagoras.
Yeah, Pythagoras, yeah, exactly. That's what he said.
See, I've been doing that for last night's class because he started pulling out random numbers. God help me.
So if we say all here, if we multiply by all, then we can multiply here also all, and all the 3 sides I can say all, right? And if I repeat that in the above triangle, then this is also square root 3 all. This is 2 times all, and this is 1 all, right? So what is a lowercase d? from there. Lowercase d is, we can add this too, right? So one side is square root 3 all. If we have 2 of those, then that means 2 times square root 3 times all, right? Because this is small d. So keep this in mind. And next here, the same thing, right? The previous slide we made d equals 2 times square root 3 times all. All is radius, right? So this is radius. All. So I would say this is 2 all, then this is 2 all, this is 1 all, this is the square root 3 all, right? So this is a small d. What is the definition of uppercase D? Uppercase D here is the minimum distance between centers of cells that use the same band of frequencies. So if we assume they are using the same band, then that is nothing but D. And this is nothing but N. How many? We have 2 cells to be used. And this is the square root 3, and this is all. If we cancel all, both sides, then d over all equals n times square root 3, which is here, right? So this one will be used here. If we assume this, if we use this formula, what we want here is the minimum distance between the centers of 2 cells, which is this. So radius is 1 kilometer. This is all. We multiply all at both sides, then here left hand side will be d, and right hand side we have square root 3 and all. So this is all. How many n? We have 12 n. Okay. So we plug that into here. Right. Actually, it should be, it should be n here altogether. So we plug 12 here, and 3 times 12 square root times 1 kilometer. 3 times 12 means 36. So 36 square root, there is a 6. So 6 kilometer. What it means here is that if we use the same frequency band here, for example, 12 here and 12 there, it should be 6 kilometers, at least. In that way, there is no interference. Same thing, 12 here, 12 there, or 6 here, 6 over there, or somewhere. Here is a 6 also. Anything that is 11, then 11 here should be that much the distance required. Okay. This is only the calculation. Other than that, until we learn about encryption, you can sit down and sit back and listen what I am trying to explain here. Okay. The architecture, cellular architecture looks like this in general. On your cell phone, it's a mobile device, mobile equipment. You have a subscriber identity module. So these days, if you have SIM card, then SIM card has its own ID. So that should be registered where? Somewhere here, home location register. Actually, home location register, not only that here, equipment identity register. So your system needs to be registered here. So when you first activate, then for example T-Mobile, then they give you, as the person assigns number to you, the number and that SIM card ID should be mapped together. So that is registered here. So your ID is in this register, and your number is in the home location register. And then we have a base station subsystem, which is the dotted box in the middle, where there is a base transceiver station. Right? This guy receive and transmit the signal to your device, between your device and this transceiver station. So this guy is generally in cell tower, right? Cell tower. So in the cell tower, there is also a base station controller. This guy receives, for example, if your device sends data signal, then this guy receives that data signal and send it to mobile service switching center. Mobile service switch center. This may be where there is a switching systems, like telephone company. And there is a MSC, mobile service switching center. If there is a data request, then from here is switched to the internet. If it is a telephone system, then it goes to PSTN, public service telephone network, something, public switching telephone network. So it switched to the voice talk. And these two others, if your phone registered the local center, then this local center immediately understands, because that is your home location, and gives service directly. However, if you are far away, if you are in Europe, okay, then of course your number is not recognized by their home location register. You are a visitor. So your number, your request comes in this visitor location, right? Visitor location register. Okay. then verify that your number was initially registered at, for example, somewhere here in America. Then it refers to the location and verify it. But every time they share that information across the countries, so not necessarily coming to their home location, but it's in the middle somewhere can be verified, so that your request can be served. All right. This is a general idea. If I pick a small piece from that architecture, then this is the case. So you are here on this car, and you're calling, right? If you call someone in another cell near you, then this guy quickly understand, oh, there's a home location register, and this guy, mobile switching center, directly switch the signal to your friend. Okay. If it's not the case, then physical location will be physical location register will be involved. This is something that I already explained there. Somebody said? We have only one lady. It looks like a lady's voice. It's not?
He can
He's talking like a
he can put his voice down.
He switch up his voice box.
Who did it? Ah, you have some skills. That kind of skills maybe interested by NSA.
Switch up the voice.
Cell phone also served the packet, not only circuit switching system, but packets. Not from the beginning, not from the first generation, but the generation, I think 2G generation, or 2.5, I think 2.5 generation. 2.5G cell phone equipped with packet-based communications. If it is a packet, then the idea is very, very similar to Wi-Fi communications that we learned last time, right? So it allows data to use channels, and data may be packed in small size. We call that packet. At this point, I want you to make sure that you understand the packet-based communication with respect to the network characteristics. For example, if there is Ethernet communication, like your internet here, so that you have 7-layer architecture, so that your data can traverse from the application layer all the way to the physical layer. Along that traverse, the head can be appended to the data sets. We call that packets. So head information is packed together with the payload data, and then each packet traveled, right? That is Ethernet based. Wi-Fi, for example, that is IEEE 802.11, That is the techniques that we learned a few weeks ago. Then it has a physical layer and MAC layer. Above the MAC layer, there is a simply controller, Wi-Fi controller. Okay, only 2 layers. Similarly, here cell phone, we have also, after we have IP-based cell phone. What is IP-based cell phone? It's not 3G but 4G, and after 5G, 6G, then we have cell phone, IP-based cell phones. So very similar to the Wi-Fi and Ethernet. But anyway, from 2.5 generation of your cell communication, we have a packet-based transmissions. So one large data can be decomposed into numerous small packets, and each packet is traversing. Okay? So at one time, packets may be traversed through this channel. Let's say if this is a time, then the earlier packets traversed here, 4 packets here, and 5 packets in another channel, and 4 packets in another channel, and then many others in other channels. So they need to reach the device of your destination, right? So the other guy, if it has a cell phone again, then cell phone receives all the signals in the reverse way that you send out. And also, each channel may accommodate not only data but voice as well, in this case, right? So it goes. So generation by generation, we can, this slide summarized a little bit of that. Initially, it was invented in Japan, by Japan, Nippon telecommunication, telegraph telecommunication. First generation. That is purely analog based. And each channel is a 30K hertz. 30K hertz frequency band lasts quite long. In this slide, immediately, it's not always the case, but so 200 kilohertz channels at the 2D. From 2D, we have digital. Speed of the communication, the first generation 9.6 kbps maximum, but at the 4G currently we have 100 megabps. Can you compare this? Let's say this is 10 kilo bps. Mega, 100 mega, then I think 10,000 times faster. Yeah, 10,000 times faster. So current data rate 10 times the data rate of first generation. From 2G, we have CDMA, multiple access. Some modulation technique has been used, CDMA. Code division multiple access. Code division multiple access uses the underlying techniques that we learned earlier. What was it? Spread the spectrum. Okay. So multiple users can send out the data or voice together with many others and modulate them and send out one signal from there. That is possible, right? That's a CDMA. So CDMA has been evolved quite much. From here to, for example, somewhere we have a CDMA 2000, CDMA 2. Initially we have CDMA 1 and CDMA 2 somewhere, and CDMA 2004 generation, and so on and so forth. From 2.5G, this is a very, very important turning point in terms of generation. 2.5G. At that time, we have GPRS, General Packet Radio Services. General Packet Radio Service. Because we have a GPRS, the data can be packed to be packets and therefore transmitted. That was invented in the year 2000, so not long ago, only 15 years ago. Okay, so packet switching became so popular, and from this generation, now everything can be treated as data. Okay, so your voice is nothing but data in technology, your voice technology. And from that point, you also have VoIP, voice over IP communications. And 3G, which is also after 2000, year 2000. The hertz frequency band is 5 to 20 megahertz, which is quite bigger than the previous, right? And then speed is up to 2 megabps. And right now, 4G was invented in 2008. The year here, the year in number right here, it's not the year it's fully serviced, right? Services come many years after the number there. So it was invented in 2008, but 4G, for example, LTE, became popular maybe 2-3 years ago, right? Since 2-3 years ago. So 2013, 14, 13 maybe, right? And we can also expect 5G. There's open wireless architecture invented in 2015, recent years. So frequency is very high, 3 to 200 gigahertz. 200 gigahertz. Still use CDMA and speed up to 10 gigabps. Speed 10 gigabps. Compare this to 4G. 4G 100 megabps, but 5G 10 gigabps. And also, engineers and scientists decided to work more for 6G. 6G technology is already saturated up to 5G. Only something that we include more for 6G is a satellite communication. What is the impact of using satellites? Right now, if you use satellites, speed is very slow. Data rate is slow. And also very expensive. Compared to your cell phone, smartphone. Smartphone is almost free, right? But you never use satellites. You can receive satellite signals only for GPS data, right? But not you're not using satellites to communication. But at the time that we have 6G, then satellites communication is involved. What is the impact of using satellites? And there is no location limitation, no restriction at all. Once you have a cell phone, then you can call somebody in deep ocean, Atlantic Ocean, or deep in the mountain, where there. I mean, currently, you cannot communicate, right, through the cell, because there is no cell tower.
Right, so it's good to have a backup and keep a satellite radio, right? Satellite cell phone.
Yeah, current satellite cell phones will be replaced by our typical cell phone by that time. Right now, satellite phones, I'm not sure, maybe very expensive. Subscription is very, very expensive. Anybody knows about satellite phone? How much is it? I mean, device itself is not expensive, but one-time call, then very expensive. What about airline? Airline uses satellite phone.
Military uses that.
Oh yeah, of course, military. Military has a lot of military satellites.
So you utilize that 6G, don't you?
No, that's a satellites. Satellite. Now, satellite and cell technology didn't meet together. By that time, they meet. Okay. So that it'll be one technology. Right now, two different technologies. So let's start with the 1G. When it comes to 1G, at that time, like late 1990s, okay, then they call that advanced mobile phone system. Advanced mobile phone system. The first generation is named advanced mobile phone systems. So don't be confused. If you say advanced mobile phone systems, oh, then maybe 5G. No, this is first G. Okay? Why they put advanced? Before they have this, all the phone systems was landline, right? There's no cell-based signals. No wireless signals. Only landed lines. So this is advanced technologies. First generation analog systems for North America, 225 megahertz bandwidth are allocated to advanced mobile phone systems. So phones signals always two different channels to be used. When you call or when you send the data, then you have two different bandwidths. One bandwidth for uploading, the other bandwidth downloading. One bandwidth that you talk to send, the other bandwidth you receive. Each market operator accommodated. Each operator is allocated only 12.5 megahertz in each direction. So in each direction, we have multiple channels. How many channels? We have 416 channels. How come you have 416 channels? That's what I ask here. Explain. Each channel is 30 kilohertz for each direction, because both the direction we have 25. But width, there is some gap between the bandwidth for forwarding and reverse, upload and download. There should be 45 megahertz interval. So for example, if you use this band to send out, then from here there, it should be 45 megahertz. So that in this case, it is download. So 12.5 megahertz, 12.5 megahertz, which means 12,500 kilohertz divided by 30 kilohertz. Then we can cancel 0 each. So we divide 12 divided by 3, so 4. So 12. We have 5 here. 5 can be divided by 3, so 1, right? So divide by 3, so we have 20, so 6, and 18, it repeated, right? More and more. So that is 416. So out of 416, 395 channels used for traffic, and 21 channels for control, paging, accessing, some other management channels. So 359 traffic channels. Quite a lot of channels. There's a first generation. GSM, TDMA, that starts from 2G, and we have 2.5G. There's enhanced communication called Edge, and then 3G. CDMA starts from here, 2D, and CDMA is evolved to CDMA 2000s, and then 4G. So some acronyms given in on this slide. So I want you to take a look at that. Multiple access scheme. As we looked and practiced a lot earlier days, that is a CDMA. Similar to CDMA, CDMA is a code division, and a lot simpler in theory is a frequency division and time division. For example, if you have a frequency here, then you can divide that frequency, right? Time also. So frequency can be divided, split it in this way. And then each frequency band, there is some interval. So this interval is so-called guard band. With no guard band, then they may be interference. There's frequency division. And time division, similarly, we have so multiple slots, and we have guard time, which means longer time we use this slot, and then there's some time interval, and we send another, and another, and another. That is the way that we use. Okay, each user is given a specific slot, no competition in cellular network. It's not like a carrier sensing multiple access in CDMA. We learned that in Wi-Fi 802.11 communication, where there is a collision, right? CSMA that technique has been developed over the Ethernet communication, like here, Ethernet communication, right? We have Ethernet lines. What is the maximum length of the Ethernet line when you do cables connect together? Maximum length? I think 500 meter, right? Each every 500 meter, you need to have some tap, repeater. And also, there's a maximum 4 or 5 repeaters to be used. So total about 2.5 kilometers or 2 miles, a little bit over 1 mile, 1.5 miles long. So every 1.5 miles, you need to have a switching a network equipment installed, not just the connector, not just the repeater, and Ethernet. So there is a, and your signals, when you send out from this to this Ethernet, then that signal travels, right? And another guy send out the signal also. So they are traveling.
Yeah, it's like a bus topology and
Exactly.
using a token.
Mm-hmm. Therefore, there is a collision.
Right.
So collision can be detected very easily if there is a line, and then resolved from there. That is 802.3 Ethernet communications. When it comes to 802.11, it's a Wi-Fi communication, then detection is not really acceptable for many reasons that we learned last few lessons. So what we need to do is, one simple way is that there's some protocols. So before you send, you need to send the tokens, say ready to send. Then receiver says, oh, clear to send. And after that, you can send out, right? And finally, you record acknowledgement. That type of protocols developed over Wi-Fi communication. Here in this cell, no competitions in time division multiple access, which means it's a time sharing. At particular time, for particular slots, there is only one user. But time, there's a slots. If you divide time more and more, then more users can use. This is time division. Code division, similar to the spread spectrum encoding technologies or modulation technologies, remains here. So I want you to recall that. See how I wrote. Refer to the CDMA technology in 04 spectrum, spread spectrum. This is the modules, right? So what happens here is that if we have two senders, data, so data bits, so the receiver one. Okay. Right. So two different data. Data here and data there, right? And then the first phase here is the spread the spectrum. So data 1 is spread out like this using chip sequence, right? Using chip sequence. This is a kind of review. I'm trying to compare three different things, right? Arrow to the 3, 11, and here for each different technologies. In this case, CDMA, I mean modulation. If you send this data 1, then in this case, the code is nothing but the chipset. If we have 1, 2, 3, 4, 5, 6, 7, 8 chipsets, chip sequences, then number 1 can be spread out 8 times. Same thing here. And they can be added together to be in one data, one signal. This one signal representing 2 data sets. Okay? So, technically you can modulate more than 2. You can modulate 8 different data or 16 different data, which means you can accommodate 8 users request or 16 users request. Doesn't matter as far as you can modulate it. Okay? And as far as, let's say this is your sender's chipset, so that your receiver has the same chipsets. This is a chipset. As far as you have the same chipsets, then you can demodulate it. You can decode it so that at the end you will receive the same data. Same data as it was sent from the sender side. That has been discussed, right? We practiced a lot for that. There's a CDMA. So we have version CDMA 1 and CDMA 2. So around that time, all the technology evolves to 2G. And then from the technology in the second generation is called the GSM. Okay, so we still use GSM. The architecture of GSM is similar to the first generation, right? Not much different. Only a little bit of more here. We have a transfer station and base station controllers. I mean, so far it's all the same, but as you can see here, there is an interface called the UM, ABs, a little bit of different interfaces. I don't know what that is, but it is the word, it is the terminologies. So when you read some articles, if it says there's not any noise, but it is called the interface. If it says A, then there is A interface. ABIS, there is an interface between BTS and BSC. So base transceiver station and base station controller. Between these two, there's some interface called ABIS. And then between BSC to MSC, this is base station controller. This is mobile service switching center. There is also interface. It is called A interface, and this is UM interface. if we discuss that interface more and more, then it'll be really out of the scope that we need to know from computer science perspective. So we don't do that. We simply see what it is, okay? And GSM. GSM it stands for Global System for Mobile Communication. And 900 megahertz operation in Europe, and in America, 1900, North America. And now around, so more than 100 countries use GSM. GSM services at the second generation, from the second generation, they already started for SMS, short message services. So we all know that, right? 160 characters, including spaces, was invented in 1985. And also GSM brings in GPRS, but GPRS was placed in service from 2.5 generations, so more effective from that time. This is packet-based. Okay, it's packet. GSM upgrades the provide IP-based packet data transmission up to 114 bps. So users can simultaneously make calls and send the data. Why? Why this was possible? Because the voice and data can be chopped into the packets. So your voice can be also multiple packets. So packets can be interleaved together to be sent out. That is possible. GPRS provides always-on internet access, and the multimedia messaging service is also possible. MMS. MMS was not available in 2G, but after, right? 2.5 and 3, of course 3. Performance degrades as the number of users increases, of course, but not the case in 4G and 5G. GPRS is an example of a 2.5 telephony, right? As I said, 2.5 GPRS. So SSM physical layer, we have, we look at this uplink and downlink, and there's some gap. If you use, for example, this channel, then there is some gap, 45 megahertz at least, so that you may, if this channel is assigned to you for uplink, then another bandwidth for downlink should be assigned, should be picked up above 45 megahertz. So, yeah, 45 megahertz. There's an uplink and downlink. So uplink, you have a packets 1, 2, 3, 4, 5, 6, 7. Those packets are going up. Meanwhile, at the same time, possibly, the packets can be downloaded. Right? So a lot efficient. 2.5G. PSC, base station, base switching, base station control. and a mobile service switching controller, and VLR, visitor location register, home location register, and many others, right? Very similar, but a little bit of modifications. GPRS, of course, maintained by 3GPP, which called third generation partnership project, 3GPP, and variable throughput and latency that depends on the number of user. Of course, right? If you have more users, then throughputs, we have lower throughputs and longer latency, and volumes of data to be transported, and quality of service is doable when you have GPRS. Okay, general packet radio services. Protocols supported by that is IP, of course, and PPP, point-to-point protocol, and X.25. With the X.25, so multimedia data can be transmitted. Teleconferencing data, media, video can be transmitted through X.25. And coding schemes, same as before, right? Frequency divisions, TDMA, so time division multiple access, and code division multiple access possible. So we have here GPRS. GPRS sits in many places. We have GPRS and GPRS. So GPRS will be main components from 2.5G. Okay. What it means to us here is that, therefore, we have we can think of the subnetwork with IP. The technology now is similar to the digital network. It's not anymore telephony networks, but digital networks. As far as we have a GPRS. So where there is a GPRS, we call that subnetwork. Similarly, we call subnetwork where there is a router. Very similar. Okay. So backbone can consider equally where you have Ethernet, Wi-Fi, cell communication where there is a GPRS, because all can be identified by IP. Okay. (3G). Much simplified. We have a base station. Previously, we have a base transfer station and base station center, but here base station, so one unit, and with the RNC, radio network controller. And in the middle, we have a MSC, like we did before, right? Mobile service switching center. And then we have a GMSC, G for gateway, So a lot of gateway function is possible when we have a SGSN, which is a service GPRS support node. So we have GPRS here. So when you have MSC, that is a switch, circuit switch domain. When you have SGSN, that is a packet switching domain. So from the 3G, we have packet switching and circuit switching together. Mainly because we have GPRS in place. Okay. CDMA, you have a wideband CDMA and CDMA 2000s. These are all encoding techniques and multiple access. So TDMA is also possible. CDMA, TDMA. Some of the encoding techniques evolved along the generation. This is also part of a CDMA, but wideband. Similar to CDMA. 4G, there's LTE stands for long-term evolution. There's a next generation currently used, right? And advantages of LTE is in two groups. For network operator, it's a high network throughput, low latency, and low operating cost, all IP network based, which is good. For end user, fast, right? So fast. And the quality of service. So the data speed increased a lot. So 1 gigabps. 1 gigabps means 1 gigabit per second. If you want to see the online video per second, if you receive 30 frames in, then that is a perfect moving objects. So 1 giga, we can say 1 gigabyte. One frame, the size of one frame, maybe one megabyte. 1 gig, then 1,000 frames can be transmitted. We need only 30. So you can compare 30 to 1,000. So high speed, super high speed.
Yeah, but
Okay.
it's not 1 megabyte per second. It's less like shipping down that, right?
During the summer, I was in the subway, South Korea. 10 years ago, when I was in subway, everybody is doing text. Last summer, when I was there, then everybody is watching TV on the cell phone. Everybody. There are hundreds of people, passengers. They're all receiving videos. I mean, real channels, TV channels. Possible.
How close the battery was?
Therefore, it is exploded in Korea. No. Samsung, the battery exploded. Okay. So all see here, the major technique is multiple access, which is modulations, encoding. So we looked at that, right? The fundamental techniques discussed. That is very, very important. Once you understand that, then anything that you do here, some division, multiple access, they all remains the same. So it is not really big issue. Only a little difference. Okay. This is the end of the cell communication technologies. Okay. Encryption. Evans these days interrupt me a lot. Okay, one more time. Okay. So not okay? This gives you the general picture of the cryptography over the cell communication. Okay, over cell communications. You have a mobile station, which is your cell phone device. Okay. So from your cell phone device, where's my? Oh, here. Okay. From your cell phone device, you have international mobile subscriber identity. Some identity, okay? ID is the same as that, right? ID needs to be sent out, right? When you call, then ID is supposed to ship, but it's very, very fast, in millisecond. In millisecond, therefore, you do not recognize. So first 1 millisecond is sent out your ID, and next 1 millisecond, 2 milliseconds, ringing and things like that. So if it is a visited network, then it goes to home network. Your home network generates triplet, KRS, okay, KRS. So like a key, well, we'll look at that. And then KRS triplets is returned, and then authentication, which is all, it's coming back to your device. Then your device encrypt the data and send it from that point. Okay, that is the idea. So the algorithms to be used in GSM for cryptography are three things: A3, A5, and A8. Three algorithms. Okay, A3, A8, and A5. So A3 is the algorithm that takes random number and then do some computation and feed into these triplets. When it computes, it takes not only random number but also secret key, user's secret key, together used to make S in this case. And another algorithm, A8, takes the user key and also random number to generate KC. And then there is a random number itself. So those three components will be a triplet, but two of these will be used for authentication, and all three of those will be fed to A5 algorithm and to make a cipher. So as you can see here, KC is a ciphering key, S is signed result, A3 means subscriber authentication algorithm, A5 is a ciphering and deciphering algorithm. This is what we want to discuss in this class much. A8 is a cipher generation. So A3 and A8 is more device dependent, so we do not do that here much. So A3 for authentication, it generates, for example, A3 takes a random number and key and generates SRS. So SRS is response to MSC, which is a mobile switching center, and mobile switching center receives that and even further send it back to your home location. A8, that is a voice privacy key generations, similar to the other. And both A3 and A8 algorithms are implemented on the SIM card, and operator can decide which algorithm to use. Operator means your phone carrier, for example, AT&T or Verizon, T-Mobile. So they are the operator, so they decide the algorithms to use. Algorithms implementation is independent of hardware manufacturers and network operators. Okay, so if you have an iPhone or Samsung phone, then they have manufacturer information, and when you activate your phone as some carrier operator, either AT&T or Verizon, then they use the manufacturer information and also their own operational policy to choose the algorithm for A3 and A8. Okay. A5, on the other hand, this is real. This is streaming data encryption algorithm. So A5 takes random number and then key to ciphering to generate ciphering sequence, and for incoming plain text will be encoded by exclusive OR operator. Exclusive OR operator. Okay. Same thing. When it is decoded, again exclusive OR operator. As far as you have the same key generated, then the ciphertext can be returned to the plain text. Plain text will be encoded to cipher text, vice versa. So your device and your destination device both are generating the same key. Okay. Once they are communicating. So A5 algorithm is a stream cipher implemented by efficiently on hardware, designed, was never made public, leaked to Ross Anderson, Bruce Snyder. So A5 1, 2, 3 has been developed, but the one that we are going to learn in this class is A5/1. There's a strong version. GSM phone uses 228 bits. That is sent in 4.6 milliseconds, which means 114 bits. Kilo bps, right? That is the speed of that. A5/1 produces 228 bits to exclusive OR with plain text in each frame. So, for example, if you talk, then every 224 bits, that much size, is encrypted with the key that is generated by your hardware according to A5/1. Encryption is very, very simple because we use only exclusive OR operator. Okay? As far as you have the right key, then decryption is not really a big issue. The problem here is that can you generate the same key? That is the issue, right? So A5 algorithm takes the 64-bit key, and then put it into 1 times 64 bits and how many of those? So that we have 228 bits. Anyway, 220 bits. When it increases that long bit, and this is the message that you want to send. So same size, 220 bits and 220 bits key, and they are applied. They are exclusive ORed here, and then cipher text is also 228 bits. When it reaches at the destination, similarly, with the exact same operation with the exact same key, so that your device and the receiver device being operated by the same algorithms. Okay, so it generates same key, streamline. Who controls that? AT&T. If you subscribe AT&T, and AT&T split that. Yeah, the techniques behind this A5 is LFSR. LFSR means what is that? It is called linear feedback shift register. Linear feedback shift register. So there is a length of the output sequence before it starts repeating itself. Linear feedback shifting register. It has n bits. So actually, in this the example we use 3 LFSR. Each one has different size. Okay, so there's a bit. If you have n bits, then it can give you 2 to the power n different states. But more precisely, it is 2 to the power n minus 1, because If there is all zeros, then it doesn't mean much. It is empty, right? So it doesn't represent any states. So excluding that, by counting all possible, then that is 2 to the power n minus 1 states. And this LFSR is based on polynomial. So you don't need to worry about. But if you say this polynomial, x to the power 12, x to the power 6, x to the power 4, x plus 1 is a polynomial, then this means x to the power 0. So according to this, you can fill each bits, right? And the bits that you consider is only this bit, 13th, 11, then that is 13th bit, right? And this is 7th bit, 5th, 2nd, and 0th. Those are the bits that we take into consideration. All right. So that is what we mean by here primitive polynomials. So actually, 3 polynomials are given. Each polynomial represents LFSR. So this polynomial can indicate the bits that we want to consider. The bits that we want to consider is really, really important. Only those bits will be counted to feedback and shift for generating the keys. That's what we are having here. So all the bits that is indicated by the polynomial are exclusive ORed, and the result of that exclusive OR operation will be fed to the entire register. And because initially all the register are all the bits in this register filled by zeros and ones, when it comes to new bits to be appended, then everything needs to be shifted by 1, right? So last bit should be shifted to 1 bit ahead. All the things. But bit shift and exclusive OR operations, all those things are very fast operator, because that is a bitwise operation. It doesn't cost nothing at all. So there is no computation time when we generate the keys according to this A51 algorithms. Okay, that's what we did. Actually, A51 algorithm uses these 3 polynomials that I wrote here, right? So these only the bits indicated by here 19, 18, 17, 14, and 0. Those are the bits that we consider. And also, this bit is very, very important. Clocking bit. This clocking bit is the indicator that that to choose which register that we want to pick for feedback and shift to operator. Okay. Here's the things for you to understand. Exclusive OR operation can be first we have to choose the register. Out of 3 register, we have register 1, 2, 3. They are not all the time to be considered for feedback and exclusive OR and shifting. 3 things, right? Exclusive OR and feedback and shift. 3 operators will be used, but not all the registers to be considered at all the times. Only 2 of those, or 3. Those are indicated by clocking bits. Clocking bits, other bits, for example, in this case, 9th bit, 11th bit, 11th bit, all the time. But the registers to be picked up only if any of these are the same bits. Any of these 3 are the same bits, then those registers will be considered. Bits, we have only binary bits, right? 0 or 1. We have 3 registers. 3 registers. Then at any times, at least 2 of those have the same bits, right? Do you see that? 0 and 1. Then we have three registers. Here is one register. In this case, bit number 8. Another register, there is a bit number 10. Another register, there is a bit number 10 again. And each bit has should be set to either 0 or 1, right? Let's say this is 1, this is 0, and the other one should be at least 1 or 0. If it is 1, then this guy and that guy, first and third guy, will be the same value. If I set to 0, then second and third will be the same value. So these clocking bits, and therefore the way that we choose register is if any register has the same value on these clocking bits, then we know that at least 2 registers always have the same values, right? 3 registers, we have 2 values, then at least there are at least 2 of them are the same. Well, at some cases, all of those have the same value, 1, 1, and 1. That is also possible, right? Or 0, 0, 0. In this case, then we can pick the register. Once you pick the register, then we need to choose, we need to consider those bits. Those bits are our concern, our interest. So we pick the bit values from those bits and apply exclusive OR. The result of this exclusive OR will be fed back to the register. But when it comes to new bits to be appended, already filled, so we have to shift 0 bits, shift to 1 bit, 1 bit shift to 2 bits, and 3 bits, and 4 bits. That is the whole idea. Okay, so let's try. Okay. All right. After we do this, and then that's it for today's lecture. and then you will expect homework assignments from me.
Oh, yeah?
Oh
You
yeah.
have to do that on Sunday. You said that we're not having homework for a month.
Yeah,
Huh?
for the Thanksgiving. You said we're not going to have it.
Oh, this is your turkey.
I'm sorry?
So this is your turkey.
You said this is our turkey.
Turkey.
Oh, no, I'm not going to have this cookie. I want the real one.
Oh, do you want the stuff? I can give you more stuff.
You said you were going to
So you can mix them.
Come on.
Turkey and stuff together.
I'll take it an early Christmas present. No homework.
Yeah.
All right, watch this very carefully. Okay, this is a real animation. Sit back and then take a look at this. Okay, so okay, we have 3 registers. So top like array. So upper one and middle one and bottom one. So register called R1, R2, and R3. Initially, we all the bits are set by ones or zeros, right? Let's assume they are set in this way. And according to that polynomial, our concern is 18th, 17th, and 18 bits, 17 bit number starts from 0, right? So 18, 17, 16, those are the bits. See, there's those color. Purple color are the bits that our concern for exclusive OR. And there is an orange color, there is a clocking bit. Clocking bit is not for computation, but that is the indicator. Okay? Indicator indicating that any of these 3 values, if they are the same, then we pick those registers. Right now, this guy has 1, this guy has 0, this guy has 1. So which ones, which registers have the same value on its own clocking bits?
1 and 3, right? 1 and 3.
First and third one, right? Because this guy 1 and this guy 1. Okay, so you understand well. And this guy is for exclusive OR operator. Here, this is exclusive operator. The result of this exclusive operator is another bit, right? Either 0 or 1. That should be fed back. So that is appended to the bit number 0. In order to insert that bit here, then we need to have space. In order to make space, everything should be shifted to left, right? Everything should be shifted to left. Then what happens? The last bit should be kicked out, right? Those last bit kicked out, and we apply those bits for exclusive OR operator.
Well, the last one because 17 should be 16, right?
No, we push. The size of a register remains the same, but only the value in it will be shifted.
One.
Yeah, 1 space. So last one will be come out. Those values coming out from each bit will be exclusive OR. Again here, that is the bits. That is the first bit of your key. First bit of your key. First bit of your key. So, given these registers, then we need to first generate the key before we do anything else. So, what is the key that you can generate? From the first register, there is number 1, right? Number 1. From the second register, we have another 1. From the third, we have a 1. If we apply this to exclusive OR, then what is this? 1 exclusive OR means 0. 0 exclusive 1 means 1. So first bit will be 1.
So these are the 3 bits that are kicked out, right?
Not yet. Kicked out, so according to shift.
Yeah, shift.
Right. We don't do that yet. Okay, we first generate the key. And then we need to come back here to see the clocking bits. So which clocks are the same? Register 1 and 3rd, right? So 1 and 3rd. So we consider 1 and 3rd. From the register 1, only those bits are our interest. So we take those bits and exclusive OR. So 1 and 0 means 1, and 1 and 1 means 0, and 0 and 1 means 1. So we generate 1. This is not considered right now, because according to this clocking bits, these clocking bits and these clocking bits are the same. So we consider here, again, the exclusive OR. 1 and 0 means 1, according to exclusive OR. 1 and 1 means 0, and 0 and 0 means 0. 0 will be the outcome of that exclusive OR operator. These two numbers should be appended to those two registers. Now we need to shift. Okay? In order to this guy get in, then first and third register needs to make the space by being shifted to left by 1, right? So everything needs to be shifted in the register 1 and register 3. So I'm going to make, see here, a little light green, and yeah, here 1, little light 1, and light 0, and that will be fed into here. So I want, for example, Edmond, you watch this if it is shifted. And Rohan, watch this if all the bits are shifted. Ready? Are they shifted? Of course, therefore we have empty at the last bits, right? Mm-hmm. And then those 1 and 0 will be fed in.
Right there, right? Oh.
Yeah, at that. What is the next step?
Then we have to.
Then we to generate another key, right?
Yeah.
From the top. So we have 0 from there.
1.
This never changed. Still we consider that. And then this 0. So
0 and 1.
0 and 1 means 1, and 1 and 0 means 1. So the next one is also 1. So 1 here.
But,
We keep doing that.
How did you choose C1, C2, and C3? Like,
That is determined. That is predefined.
that's going to be in homework predefined too, right?
Yeah. See here? I give you polynomials and clocking bits. No, more than that. I give you initial bits. I give you that. Then you can generate, if I said, give me 4 bits of key, then you need to iterate 4 times.
All right. Are you going to post this one in that book?
It is already.
Yeah, but like what we're doing here, the recording, with the slides, that would be good.
Animation?
Yeah, yeah.
Sure will do.
All right. Because like we're in class and we're seeing it and everything, and then we know how it went.
Edmond is so aggressive.
I'm
I will.
No, but like, say, okay.
Okay. So that animation slide will be posted, but I forgot. But our students are so great, they never forget to request. Every semester. Initially, I do not post, but in response to your request, I post. The animation slide will be posted. This PowerPoint
Yeah. With
That
navigation
page,
and
that
everything.
page.
Yeah.
All right. Any question? If you have any question, review my lecture video and read the course material and do homework. Okay.
We're gonna have
So-
for sure, right?
So I think this is enough Thanksgiving gift to you.
I expected more.
Not such a good
Yeah. If you need more stuff, I can give you.
That was good.
How did you get? One second. That 18, 17, 16. The purple ones, right? Those are back in the back slides, right? How did you get them?
Those are the poly.
Yeah.
It's a given, but numbers are from
These
the
columns- How did you
polynomial.
get these?
Polynomial. Remember that? Hold on.
Back? No, this was.
I cannot.
Keep.
I don't know.
Keep. Just
No. Okay, here. Come. Oh, no.
You just deleted the animation. How are you going to put?